Hello everyone, I am Senqiao from Harbin Institute of Technology, Shenzhen. The title of our paper is A UniverApproCNN Neural Networks with Universal Approximation and Explicit Training Strategy. Approximation theory has achieved many results in the field of deep learning. However, these results and conclusions can rarely be directly applied to the solution of practical problems, or directly get the training and optimization of deep learning models in the actual context. To address this issue, we construct a convolutional neural networks structure with universal approximation, which is called UniverApproCNN neural networks. It is ensured that the optimization area of such convolutional neural network is bounded by an explicit approximation upper bound that relies on the hyperparameters of this model. Moreover, a general case of multidimensional is considered by generalizing the conclusion of the universality property of convolutional neural networks. A practical problem in the field of inertial guidance is used as a background to conduct experiments, so that the theory can give an explicit training strategy and break the barrier between the theory and its application. We use the curve similarity index defined by free chat distance to prove that the experimental results are highly consistent with the functional relationship given by the theory. On this basis, we define the optimization coefficient of UniverApproCNN neural networks, which can give the stop time of model training and related training strategies. Specifically, taking the operation of normalization as a widely used technique into consideration, we then show that this operation does not take effect on the optimization performance of the convolutional neural networks and the UniverApproCNN neural networks. In the 1980s, the neural networks model received people's attention again because of the successful applications such as on signal processing and control. The dense problem naturally arises from these applications, but what properties does the activation function need to make it dense in the corresponding function space? This denseness is considered to be fundamentally important in neural network theory as the theoretical ability of approximation. For the single-headed layer perceptual model, which is one of the more simpler neural networks modeled mathematically, Pincus has made a detailed summary, including approximation bound with different activation functions and under different norms. For networks with a certain depth and spatial connection structure with sparsity compared with their success in practical applications, there is relatively little research on their theoretical approximation capabilities. Although there are some theoretical interpretations for superior behavior due to their depth and spatial connect structure. Recently, Zhou Dingxuan proved that the deep convolutional neural network is universally approximated in the continuous function space, and given the upper bound of approximation under certain conditions. Based on this, we carried out our work. At first, we proposed the construction of a generic convolutional neural network with explicit approximation bound. which is called the UniverApproCNN neural networks model. After that, we generalize the conclusion of the universality property of convolutional neural networks to a general case of multi-dimensional datasets. We show that the approximation performance of convolutional neural networks and UniverApproCNN neural networks with batch normalization operation will not be weakened at least. Then, we prove the universality of approximation and model design of convolutional neural networks suitable for two-dimensional input. Look at this picture. It shows the structure of UniverApproCNN neural networks model and the sliding mode of convolution kernel. Since the structure of the model completely conforms to the universality theorem and the condition of sufficient training, theoretically, when the hyperparameters of the model change, in addition to the structure of the model itself, its corresponding approximation upper bound also changes accordingly. The corresponding relationship between these two chains can guide us to get the ideal training strategy in the experiment. Then, in order to verify the relationship between the approximation bound of UniverApproCNN neural networks and related parameters, we designed an experiment oriented to inertial guidance area. We use the UniverApproCNN neural networks model to approximate a complex model in this area. Our experimental object is a trajectory restoration model based on inertial sensors. The input is 3-axis acceleration, 3-axis angular velocity, and the output is the spatial position of the object's movement. Regarding the model as a mapping from input to output, the mapping relationship is the object we want to approximate with UniverApproCNN neural networks. At this time, we need to generate a dataset based on a large number of variable parameters during the movement for training, verification, and testing of the UniverApproCNN neural networks model. What's more, in order to enhance the credibility of the experimental results, we independently predict the motion trajectories of objects in different directions. That is, use a parallel experimental method to predict the motion trajectories of x, y, and z axes. These pictures show that the experimental results are highly consistent with the functional relationship given by the theory. Not only that, to measure the degree of agreement, we use friction distance to define the similarity index between the experimental results curve and the theoretical curve. After checking the similarity of the result curves of the three experiments, the agreement between the experimental results and the theoretical values reach 96.45%, 95.76%, and 98.31% respectively, which completed the theoretical verification. Look at this picture. As the model parameter m changes, the scale and the performance of the whole model are changing accordingly, so the applicable training strategy will also continue to change. It can be seen that When m is small, the model converges slowly. At this time, we need more iterations. However, as m increases, the model converges faster and faster. At this time, if the number of iterations is not appropriately reduced, there will be overfitting. The change of m causes the number of training iterations to also change instantly, although this brings inconvenience to the experiment. This feature also reveals the relationship between m and many hyperparameters in the training strategy, such as epoch, batch size, and learning rate. If we can analyze the relationship through some methods, then we can formulate a rigorous and effective training strategy for the hyperparameter adjustment of the model. So, we defined the optimization coefficient of UniverApproCNN neural networks, which can give the stop time of model training and related training strategies. Through simple structure text errors, combined with the curve similarity measure we defined, we can determine the value range of the approximation coefficient and then predict the possible errors of the complex structure deep learning model in the test site. So, if the test error of the model is always significantly larger than the error range predicted by us during training, it means that the training is not sufficient, and we need to increase the number of iterations. On the contrary, it shows that the training effect has reached a good level, and the training should be stopped at this time. Otherwise, the situation of overfitting may appear. To sum up, we build a bridge between model design, model implementation, model training, and approximation theory by defining approximation coefficient, so that the relevant conclusions of approximation theory can be applied to specific experiments. In the future, it can also be extended to more research on models and approximation theory, so it has high application value. Finally, I would like to summarize our work. We propose a convolutional neural networks model supported by related approximation theory, UniverApproCNN neural networks. We successfully applied it to the object motion tracking problem in inertial guidance theory, and successfully verified the relevant conclusions in the approximation theory. In the process of verifying the relationship between the optimization bound and the network structure parameters, we discovered the relationship between the training strategy and the network structure, and we successfully used this relationship to guide the training of the model. As a deep learning network, although it has sacrificed performance, it has made significant progress in interpretability, and this interpretability can guide the formulation of model training strategies very well. In the future, we can use this as a basis to optimize performance to enhance its interpretability while ensuring performance, or use this solution as a basis to find a balance between the performance and interpretability of more deep learning models. Okay, that's all. Thanks for listening.